Hello students and welcome to the lecture. So students, as we know that in the previous lecture, we had started our discussion over the elasticity, right? And that was our part 1. In this lecture, we are going to continue the discussion over the elasticity and that is going to be our part 2. If we talk about the elasticity, like in the previous lecture, we had discussed that elasticity is actually the ability of a body to regain its original shape, size, and you can say the original or initial configuration after the removal of external deforming force. Okay. And in this lecture, basically, we will going to talk about the stretching of rubber, factors affecting the elasticity, and at last, we will see the summary of all of this. In the previous lecture, we had talked about the, you can say the terms related with elasticity. We have talked about the stress, types of stress. We have talked about strain, types of strain. We have talked about the elastic limit. We have talked about the Hooke's law. I hope you have gone through these topics in the well enough manner. You have revised them before you have come for this lecture. As many times I reminded you, it's for your own benefit. So if you are doing this on the regular basis, the thing will be in your favor. If you are not doing this on the regular basis, the thing might be against. Okay. So before starting this lecture, as usual, we have our small disclaimer over here that we are required to understand before we proceed further. So the disclaimer is like the images used in a slide deck are for educational purposes only. We respect the intellectual property rights of the original creators and owners of these images. If you are the owner of any of the images used in this deck and have any concerns or issues, please contact us at sathee@iitk.ac.in and we shall remove the image. Now, let's begin with the stretching of rubber. So when load is applied to stretch a metallic wire and rubber band, the result of stretching in two cases are quite different from each other. So we are saying that basically if we take two things, one is the metallic wire, second is the rubber band. And if we apply the load of force to stretch them, so basically the results in these two cases that we will observe later, these two cases will be quite different from each other, right? And if we compare these two, then we could say in order to produce even a small strain in a metallic wire, the force to be applied is very large. Like you can say if you are holding any metallic wire in your hand and if you want to stretch it, okay, so the strain that you have to apply, the force that you have to apply on this metallic wire to stretch it, that force will be of very large magnitude. In case of a rubber band, even a feeble force produces a very much strain. Like you can say if you take a rubber band and if you try to stretch it, you could easily stretch it. You could easily, you can say produce a strain in that rubber band to stretch. But in case of metallic wire, you have to apply a large amount of force, then only you could do it. Okay. A metallic wire can regain its original length up to a strain of 0.001 or when the increase in length is 0.1 of the original length. So like you can say if you are having a metallic wire of 1, for example, you're having a metallic wire of 1, then up to 1.1, that is the maximum length you could stretch it or you could generate a strand inside it so that it could regain its original length once the deforming force that you are being applied on it removes. A rubber band could regain its original length up to strain as large as 10 or when the increase its length is 10 times its original length. So like you can say, if you are having a rubber band of X length up to 10X, you could generate a strand in it and even at 10X, it could regain its original length. Got it? So basically now you can say that the ability to regain the original shape is higher in the terms of rubber band and it is lower to the metallic wire in comparison with the rubber. Like if you are having the metallic wire of length 1, you could only stretch up to the 1.1. You could only generate a strain up to 0.1 so that it could regain the original length. Okay. In case of rubber band, if you are having a rubber band of X length, you could even stretch it up to the 10x or 10 times its original length. Even it could regain the original position. Got it? The value of force that could be applied to metallic wire to stretch it within elastic limit is very large. Okay. Like you have to apply a very high value force to the metallic wire to stretch it even in the elastic limit. Okay, if you cross that elastic limit, the metallic wire is not able to regain the original length after removal of deforming force. Whereas in case of a rubber band, the elastic limit is crossed even on applying a feeble force. Like if you are stretching a rubber band and if you applied a little bit more force, the rubber band could easily cross the elastic limit. Okay, because the force that is required to generate a strain in rubber band is much more smaller in comparison with the force required to generate a strain in the metallic wire. Okay, so in the case of metallic wire, if you want to generate a strain or stretch within the elastic limit, you have to apply a value of force in a very large quantity. Whereas the rubber band elastic limit could be easily crossed even on applying a feeble force. Got it? Now the stretching of rubber further. The behavior of rubber. Due to its complex structure, the elastic properties exhibited by rubber are altogether different from those of metal. Like you can say, the rubber having a complex structure. So that's why it's having that kind of elastic properties that could be different altogether through the metal. Rubber is a natural polymer made of a long chain molecules. In the normal state, the molecules are bent back and forth and are tangled together. Okay. The force that holds the atoms together within the molecule of the rubber is stronger than the force that holds the rubber molecules together. Okay. Or we could say the force that is actually holding the atoms together within the molecule of rubber is much more stronger than the force that holds the rubber molecules together. So within the molecules, the atoms are more strongly connected to each other than the molecules outside in rubber connecting to each other. Okay. Therefore, when you stretch a rubber band, the molecules straighten out and allow the rubber band to become longer even up to 10 times its original length. Why? Because the molecules outside the configuration is having a long force attachment but loose long force attachment. Like these are loosely connect to each other, so they could be easily stretched out up to the 10 times of the original length. And inside the molecules, the atoms are present. These are that much connected to each other that they could easily connected with each other or could remain connected to each other even the deforming force is being applied up to the 10 times. The limit is reached when the molecules are fully stretched and become almost parallel to each other. When molecules become parallel to each other, it is the condition when we could say molecules are fully stretched, and now we could say the elastic limit has been reached. Okay. When the stretching force is removed, like we could say when the deforming force that is actually being deforming the rubber removed, the molecules of the rubber tend to curl back again like they were. Okay. Because of the attraction and cross links between the neighboring molecules. Like when we stretch them, so basically we are breaking their curling, okay, and we are making them parallel to each other. And once this parallelity reached, this is the elastic limit. So when you remove the deforming force, again the molecules will start curling back again because of the attraction force and cross links between the neighboring molecules. It may be pointed out that the rubber comes to the original length even when its length is increased several times the original length. So like you can say, if you are holding any rubber band, okay, and it is having some length. So if you stretch it further, okay, you could say that it could be stretched easily up to a very large limit. And then if you just pull the force back, if you stop stretching it, and if you leave it loosely, you could say it could easily gain its original position, right? So rubber having a tendency to regain the original length easily even after got stretched for a several times length. Thus, the rubber has large elastic limit, but it does not obey the Hooke's law. Hooke's law is like strain equals to strain, sorry, stress equals to strain. So rubber having a large elastic limit, although, but it is not obeying the Hooke's law. Materials like rubber, which could be greatly stretched, are called the elastomers. So if the question is like, what do you mean by the elastomers? So remember, elastomers are that materials which could be greatly stretched without got break. Okay, so these are the elastomers. Further, rubber does not having any plastic range. Just remember this, rubber does not have any plastic range further. Okay, therefore it just breaks when stretched beyond certain limit. Okay, like if you continue stretching and the stretching reaches the limit, and even if you continue to stretch and that limit is crossed, then basically the rubber will get break. Okay, so that's why if you're holding a rubber band and if you stretch it up to a certain limit, you will find out that the rubber has been fully stretched. From that point, if you continue it further, the rubber band will break easily. Okay, now bulk modules or bulk modulus. It is defined as the ratio of the normal stress to the volumetric strain. It is noted by letter small k. Thus, k equals to normal stress by volumetric strain. Got it? Consider a sphere of volume V and surface area A. Suppose that a force F, which acts uniformly over the whole surface of sphere, decreases its volume by delta V. Okay, then K equals to minus FV by A into delta V. Okay, the negative sign that we have just seen, it actually indicates that on increasing the stress, the volume of sphere decreases. So because it's not having any positive connection, like increasing the stress does not increasing the volume of sphere. On the contrary, increasing the stress is actually decreasing the volume of sphere. So that's why this negative sign is being shown up here. Now, F by A equals to P, the pressure applied over the sphere. Okay. Therefore, K equals to P into V by delta V. The units of bulk modulus are pascals or Newton meters power minus 2 in SI. Thereafter, the compressibility. So the reciprocal of bulk module of a matter is called its compressibility. So what do you mean by the compressibility? Just an you can say reciprocal of bulk modulus. Therefore, compressibility is equals to 1 by K. The units of compressibility are reciprocal of those of the bulk modulus. Therefore, the units of compressibility are pascals power minus 1 or Newton's power minus 1 into m square in SI. Now, modulus of rigidity. So what is the meaning of this? Actually, it is defined as the ratio of tangential stress to shear strain. Ratio of tangential stress to shear strain. It is also called as a shear modulus. It is noted by the Greek letter eta. Thus, eta equals to tangential stress by shear strain. Considering a rectangular block, here you can see in this picture, whose lower face ABCD is fixed and upper face EFGH is subjected to the tangential force F. Like you can say, this face ABCD is actually fixed, but this face is facing the tangential force. So now you can say this is actually going further. Okay? It is being represented by the dotted line. Let A be at the center of the each face and AF equal to L be the perpendicular distance between the two faces. The tangential force will shear the rectangular block into a parallel pipe by displacing the upper face through a distance F into F equal to X. Say if angle F into AF equal to theta, then theta is the angle of shear. So N equals to F by A by theta equals to F by A into theta. From delta AF we have tan theta equals to F into F plus by AF equals to X by F. For solids, angle of shear is very small, therefore tan theta equals to theta equals to X by L. Got it? Now, the distance X through which the upper face has been displaced is called the lateral displacement. Therefore, the shear strain may also define as the ratio of lateral displacement of a layer to its distance from the fixed layer. The units of modulus of rigidity are also pascals or Newton meters power minus 2 in SI. There is a note. A solid develops restoring force whenever it is deformed in size, length, or volume or shape. Whereas in fluid, the restoring force is set up only when its volume is changed. That is why a solid exhibits all the three types of elasticity and the fluid possesses only volume elasticity. Delay in regaining the original state by a body after the removal of the deforming force is called the elastic after effect. In galvanometers and electrometers, the suspension made from quartz and phosphor bronze are used as the elastic after effect, negligible in wires of these materials. So, the elastic fatigue is defined as the loss in the strength of a material. Why? Because it is caused due to the repeated alternating strains to which the material is subjected. Now, Poisson's ratio. Poisson's ratio is equal to lateral strains by longitudinal strain. If length increases, then the radius of wire decreases. Poisson's ratio is a unitless and dimensionless quantity. It's not having any unit as well as dimension. There is a note. The theoretical value of Poisson's ratio for all substances lies in between -1 and +0.5. But the practical value of Poisson's ratio lies between 0 and 0.5. Now the factors that really affecting the elasticity, if we talk about them, like there are the several factors through which the elasticity of any material could be affected. First is the effect of hammering and rolling. So hammering and rolling result in decrease in the plasticity of the material due to the breakage of crystal grains into smaller units and has elasticity of material increases. So we can say that the crystal grains that are being presented in a larger size in the metal, okay, that having some plasticity, by doing the hammering and rolling, actually we are brittle this, you can say the crystal grains into a smaller units, and that's why the elasticity of the material increases, but the plasticity of the material decreases. Thereafter, the effect of annealing. Annealing results in increase in the plasticity of the material due to the formation of large crystal. Hence, the elasticity of the material decreases. Now, effect of the presence of impurities. The effect of the presence of impurities in a material could be both ways. Therefore, it could increase as well as decrease the elasticity of the material. Like we can say, the presence of impurities is not having any defining area. Like if the substance having the impurity, its elasticity will decrease. Nothing like that. It is depend whether the elasticity may increase or may decrease. The type of effect depends upon the nature of the impurity present in the material. Okay. Thereafter, the effect of temperature. In most cases, the increase of temperature of the material causes decrease in the elasticity of the material. Why? Because when the temperature of a material increases, so the molecular forces got down because the kinetic forces of the molecules got increases. So that's why the molecules started running apart from each other, and the force of attraction weakens amongst them. So that's why the increase of temperature of the material decreases the elasticity of the material. The elasticity of the inward does not change with the change of temperature. Okay. The module's elasticity has same units and dimensional formula as that of stress or pressure. The material is more elastic if its value of modulus of elasticity is large. Young modulus elasticity by modulus rigidity eta exists only for solids, as liquids and gases couldn't be deformed along one dimension only, and also so couldn't undergo a shear strain. However, the bulk modulus of elasticity B exists for all the three states of matter like solid, liquid and gas. The solid are more elastic and gases are least elastic. It is so because the given stress applies to the gas are more comprehensible that of solid. The two are moduli of elasticity of gases, isothermal elasticity and adiabatic elasticity. It is found that at given pressure P of air, the value of isothermal elasticity is equals to P and adiabatic elasticity equals to V into P, where EA by EP equals to CP by CV is greater than 1. So, E0 is greater than the EI. Young modules of material of a wire is numerically equal to the stress, which will be double the length of a wire. Thereafter, elastomers we have just you can say covered it in the previous lecture. These are those materials for which stress and strain variation is not straight line within the elastic limit. These materials do not obey the Hooke's law over most of the regions. Such materials have no plastic range. The breaking point lies just close to the elastic limit. Examples are rubber, the elastic tissue of aorta, the large vessel carrying blood from heart, etc. Ductile materials. Now, what do we mean by this? So these are those materials which show large plastic range beyond elastic limit. For such materials, the breaking point is widely separated from the point of elastic limit. Okay. Brittle materials. These are those materials which show very small plastic range beyond elastic limit. For such materials, the breaking point lies close to the elastic limit. Such materials couldn't be used in making the springs and sheets. For examples of brittle metals are cast iron, glass, etc. Here we have finished the topic. Now it's part for the summary discussion. We have talked about the stretching behavior of metallic wire and rubber bands. Metallic wire we have talked about, rubber bands we have talked about, like what quality the rubber band exists and when it got break after overstretching. Key concepts we have talked about like bulk modules, compressibility, module rigidity, portions ratio. Factors affecting elasticity we have talked about like hammering and rolling, annealing, impurities, temperature. And also we have talked about like elasticity is higher in solid than in gases. Elastomers we have talked about, ductile materials we have talked about, and examples we have also seen. So with this, we have finished this lecture. It is requested to all of you kindly revise the facts and figures that all we have discussed in this lecture and keep yourself ready for the next lecture. With this note, let's end this lecture and thank you.